Hello and welcome. Today we'll be discussing Cambridge O-Level Physics paper number 2. This is the theory part and this exam is May-June 2021. This is version number 1 of the exams that were held in May-June 2021. The subject code for this exam is 5054. Let's start. So the first part, section A. So we have to answer all the questions in this section. So first question, an aircraft flies at a constant height. The air drag and the force from the aircraft engines together produce a force on the aircraft of 36 Newton due north as shown in figure 1.1. The wind produces a force of 12 kilonewton towards east. This is the 12 kilonewton force towards the east, and this is our figure. So draw a scale drawing to show the resultant force acting on the aircraft. Use your drawing to determine the size of the resultant force and the angle between the resultant force and the north. Okay, so remember, so in order to solve this question, you have to use a rule or a ruler, pencil or your pen, and a protractor. So first of all, we draw a not to scale diagram for this thing. So we have 36 kilonewton force acting in this direction, and we have around 12 kilonewton force acting in this direction. So from our analysis or from our observation, we can see that the resultant force will be this. So this will be our resultant vector. Just use the vector combination to solve this, and this is a right angle triangle, and if we want to calculate these values, we can always use the Pythagoras theorem. So for example, resultant force is 36 square plus 12 square whole under root. This will give us the value of resultant force. The value will be around 37.947 kilonewtons. And if we want to calculate this angle, say we call it as theta r with respect to north. So first we have to calculate this. So the theta can be given as tangent inverse of 36 divided by 12, and for theta r you can just simply minus, I am doing it here. So theta r is just simply 90 degree minus theta will be your value. This will be something around 18.435 degrees. So this is the mathematical way of solving it. But here we have to use ruler, pencil, and protractor to actually draw this vector scale, draw these vectors and find out the resultant force. So first of all, we defined a scale. That is very important, scale. So a good scale to use is 1 centimeter on your rule should be representing 4 kilonewtons. This is a good scale to use. So if you just simply draw the lines, so this line will be 3 centimeters, and that is equivalent to 12 kilonewtons force, and this line will be 9 centimeters. So I draw it a little longer. So this is say 9 centimeter, and that is equivalent to 36 kilonewton of force. And make sure that this angle is 90 degrees. And then just simply you have to find out the resultant vector. Just draw this vector at this point and draw a line that matches these 2 points. And then once you draw this line, you just measure this length. Measure, say for example, I call this A, B. So you measure AB using the ruler. So you measure the length AB using the ruler, and if you measure this, this will come out to be something around 9.4 to 9.5 centimeter. It will be something around this, or um, you can also say that this is something between 9.3 and 9.5 centimeter. So because some plus minus, or no, not plus minus, but it will be something in this value. And once you have this value, so just multiply this value. Say you get so the resultant force, say you get 9.4 centimeter, multiply it by 4 kilonewton, and this will be your resultant answer. So resultant answer will be around 37.9 or 38 kilonewtons, something like this. Similarly, now this was our north direction. So the north direction was given. So this was the north direction of the compass. So we have to measure this angle. So theta r, say theta r. So just simply measure this theta r. Again, measure theta r. So if you measure this angle, this theta r will approximately be equal to 18.5 degrees, or something between 18 and 19 degrees is the right answer. So if you put values over here, so just something you can write 18 or degrees or 19 degrees. So any value between these, or any of these values, will be considered as a good answer. And again, if you have to check, you can always do this analysis. This is the mathematical analysis to check your answers. So this is how you solve this. The next question. So the next question says the acceleration of the aircraft is uniform. Describe how a uniform acceleration differs from a non-uniform acceleration. So let's just simply draw the two graphs. So this is for velocity, this is time. So, so for a for a uniform acceleration, the velocity time will look something like this. Acceleration is constant. And for a non-uniform acceleration, the velocity time graph will look something like this. Say something like this or this. So this is the acceleration is not constant. So this is the primary difference for a uniform and a non-uniform acceleration. So if we have to write it, so we can write it as for a body in motion, uniform acceleration acceleration results in constant. See, this is constant acceleration, whereas non-uniform acceleration results in changing acceleration. So this is the simplest way to describe it, and you can also say that say graph A, and you can also label graph B. Graph A shows uniform acceleration, and graph B shows non-uniform acceleration. You can easily say like this. And also it's better to say velocity here and velocity. Write down velocity here as well. That will make things much easier. So this is how we can say that. Other than that, we can also, if you have to write some other points, you can say that for uniform case acceleration, sorry, speed or velocity increases at constant rate, and for non-uniform acceleration the speed and velocity doesn't increase at constant rate. So these are another points which you can write in the same answer. Okay, so next part, it says the mass of an aircraft is 60,000 kilograms. Calculate the acceleration of the aircraft. So we know that force equals to mass into acceleration. So mass is 60,000 kgs. Force, remember the resultant force acting was 37.9 kilonewtons, and you have to find the acceleration. So acceleration will be 37.9 kilonewtons divided by 60,000. It is approximately 0.632 meters per second square. So your answer will be 0.632 meters per second square. So remember, do not forget to write the units. So these are very important. And always give your answers up to 3 decimal places. That is also a good scientific practice. Okay, next question. So the next question, it says in figure 2.1 shows a hollow metal cube filled with boiling water. The temperature of 4 vertical surfaces are equal, but each surface has different color or texture. So this is your surface, say 1. This is surface 2. The surface at the back of side is surface 3, and the surface on this side is your surface 4. So they are talking about these 4 surfaces. So a metal radiation sensor is placed at some distance from each surface, and the metal reading measures the thermal radiation emitted from each surface. The results are shown in figure 2.2. Draw a line linking each type of surface with appropriate meter reading. One line has drawn for you. So first it says shiny black is 80 degrees centigrade. So remember, shiny surfaces are good reflectors of radiation as well. So again, black is a good absorber of radiation. So it means that the temperature will be higher. So on 80 side. Similarly, dull black. So dull surfaces are poor reflectors, and it is a black surface, and it means that the temperature will be more than the shiny black surface. So the answer, the best it would be this one. Similarly, shiny white and dull white. So shiny white will have lesser temperature than the dull white. And similarly, the shiny white surface will also have less temperature than the black surfaces. So shiny white will be having amongst the two 40 degrees is lesser. And similarly, dull white will be 60 degrees. So this is how you will be drawing your lines. Next part. The hot surfaces produce a convection current in the air outside the metal cube. Describe how the convection current is produced. So, for example, this is your cube, and say this is the air around the cube, and the convection current would be something like this. So what happens? So air around this surface will heat up. The hot air is less dense than the cool air, so the hot air will rise. The cool air from the surrounding comes to take its place, and that basically generates a convection current. So that now we have to write this whole thing in words. So the say air around the surface is heated. The heated air or heated air or hot air becomes less dense, which allows it to rise. The cool air in the surroundings comes to take the place of hot air. This results in a circulating current or convection current around the surface of the metal cube. So you can also write that the air around the surface is heated because of convection. So heat transfer occurs because of convection. Also radiation as well over here. Convection because of no, I mean, but just it even it's better if you just ignore this line as well. It will make a little more complication. So this is uh, a good answer. So we have to basically write down three key points here. The first key point is that air must be heated. The hot air is less dense compared to the cool air, and the hot air rises. And since the hot air rises, the cool air comes in place of the hot air, and that basically starts a circulating current. So this will be our complete answer for this game. So next part, it says that a hot steel rod is cooled by plunging it into water, as shown in the figure. The steel rod has a mass of 2 kg and is initially at temperature 500 degrees centigrade. It cools to 550 degree when placed in water. The specific heat capacity is 460 joule per kilogram per degree centigrade. Calculate the thermal energy slash heat lost by steel rod as it cools to 50 degree centigrade. So we remember just simply Q equals to mc delta T. This is the formula of heat energy or thermal energy that is lost due to this case. So mass is 2 kilogram, specific heat capacity of steel is 460 joules, and change in temperature, remember 50 degree minus 500 degree minus 50 degrees. So this is 2 multiplied by 460 multiplied by 450. So the overall value will be 4140 joules, and we can also write it as 414 kilojoules. So thermal energy 414 kilojoules. Remember, do not forget to write the units. Units are very important, else you will lose marks. Next question. It's next part of the same question. A small mass of water boils when the rod is placed in the water. The remaining water then cools to room temperature, and some of it evaporates. In boiling and evaporation, water molecules escape into the air. State one way in which boiling is different from evaporation. So remember, boiling occurs at boiling point only, whereas evaporation occurs at all temperatures. Similarly, remember evaporation, another point, occurs only at the surface of the liquid, whereas boiling occurs throughout the liquid. So this is important. So you can write any of these 2 points, and these 2 points will, or any one of these 2 points is good for securing complete marks for this part. Then it says the rate of evaporation decreases as water cools. Explain why this happens using the idea of molecules. So, so the what happens when cooling occurs? So when cooling occurs, the molecules loses their kinetic energy. They become less vibrant, and in this process, less molecules escape the surface of the liquid, and eventually your evaporation rate decreases. So let's write it down. The molecules lose their kinetic energy. So this becomes, therefore, less number of molecules will have energy to escape the surface of the liquid. This decreases the rate of evaporation. So these 3 parts, or these 2 or 3 points, will be enough for you to secure complete marks. Remember, molecules lose their kinetic energy, or the kinetic energy of the molecule decreases, less number of molecules will be escaping the surface of the liquid. These are the 2 points for which your 2 marks will be given to you. So next question. So next question, question number 4, it says figure 4.1 shows a curve on a rope, and figure 4.2 shows a wave on a spring. Both waves are moving in the direction as shown by the arrows. State the name of each of the two waves as shown. So remember, this wave in figure 4.1 is a transverse wave. So the waves on a rope are, these are transverse wave. And similarly, this wave in a spring is a longitudinal wave. Longitudinal wave. Okay. So remember, the particles move up and down, and in longitudinal wave they move in this direction. So this is the easiest or easy way to see how this thing or how we name each of these waves. So on figure 4.1, draw a wave which is much smaller frequency than the wave shown. So frequency. So remember, uh, velocity of a wave is equal to frequency times wavelength. So much smaller wave, or much smaller frequency means higher. So smaller frequency results in higher wavelength. So what is the wavelength? So for example, wavelength in this of this wave is say lambda 1. So our resultant wave must have lambda 2 greater than, so lambda 2 should be greater than lambda 1. So the lambda 2 is the wave which we are going to draw. So for example, let's draw on the same wave. So let's say your peak starts from here. So this case, say this is your peak point 1, this is your peak point 2. So the overall lambda is lambda 2, right? So my lambda 2 is greater than lambda 1. So this is the 4 part 2. So this is the wave I have drawn. So wave I have drawn, it would look something like this. And you also mentioned lambda 2 greater than lambda 1. That will also uh, tell your examiner that you know the concept and you know the answer to this question. So describe the movement of point X on the spring as shown as the wave passes. So the point X will move in this direction and in this direction. So as the wave passes, it keeps on oscillating in this right left fashion, or you can say that parallel to the direction of force, or you can also say that back and forth. So the good way to write it as parallel to, oh sorry, let me write it completely. The point X will move parallel to the direction of the wave. You can also say, um, let me write it here, right, left motion, or back and forth, back and forward, you can say. Also it's good, but a good way or good scientific way to write it as, or good technical way to language to say it as parallel to the direction of wave. Okay, so next part. So question number 4, or sorry, table 4.1, question 4 part B. It says table 4.1 shows some sentences that student writes about waves. His teacher places a ring around each mistake. Write a suitable correction for each mistake. One is done for you. So sound travels 3 into 10 power 8 in the air. So sound travel speed is 330 meters per second in the air. This, or the other mistake is electromagnetic waves travel at 3 into 10 to power 8 meters per second. Similarly, sound is higher pitch. Sound with a higher pitch has a larger amplitude. No, the light has a larger frequency. X-rays are used for prenatal scanning. No way. These are sound waves, or very exact ultrasound wave. Ultrasound waves are used for prenatal scanning. In electromagnetic spectrum, microwaves have the highest frequency. No, gamma rays have the highest frequency. Gamma rays. Remember, gamma rays, X-rays, ultraviolet rays, visible light rays, then come microwaves. So it is a kind of, they are on the other side of the spectrum, on the lower end of the frequency, microwaves, then you have um, uh, radio waves and things like that. So this is how it goes. So next question. Question number 5 says figure 5.1 shows array of diagram of lens being used as a magnifying glass. Three rays are shown coming from top of an object O. The points labeled F are one focal length from the lens. The point label F is one focal length. So F is the focal length of the lens. Okay. State the name of this lens. So this is a convex lens. Remember, so this is a convex lens or a converging lens. So name of the lens, if you can also write convex lens, or you can write converging lens. Then it says, describe what happens to the ray of light R. So ray of light R. So what happens to this light? So this ray of light happens R as it enters the lens. So it is entering from air. This is your lens. This is again your air. So air is a less dense or a rare medium, rarer medium. Lens is a denser medium. Again, air is a rarer medium. So when the light enters from rarer to denser, it bends towards the normal. Okay, so just simply say as it enters the lens, it bends towards the normal, or you can easily draw this normal over here as well. So just draw a tangent here, and this will be your normal. Similarly, bends towards the normal as it is entering from rarer to denser medium. You can also write it the speed of light decreases. This is also fine, and this is the reason why we see um, the rainbow effect, that the speed of light as it enters a medium, every frequency is affected, or the speed is so v equals to f lambda. So the velocity or the speed of light, so we call it as c equals to f lambda. So when the speed decreases, so every frequency is having different speed, and therefore we see the constituent colors of white light in rainbow. Similarly, as it leaves the lens, so it leaves the lens, it says that so as light enters from denser to rarer medium, it bends away from the normal. So this is, say, your diagram, and this is your normal. So this bends away from the normal. It bends away from the normal as it enters from a denser to rarer medium. And similarly, the speed of light increases. So this is the right answer, the best way to write these answers. So next part, using all the rays from O, complete the figure shown figure 5.1 to show the image formed. So remember, it is the magnifying glass, so the image is formed on the side where we have our object. So just simply extrapolate these two. So one of these line is already extrapolated for you, and extrapolate this line, say, on the back, and your image will be some place here. remember, some of the people make the mistake, okay, find this and make it somewhere here. So this is not the way. Do not do this mistake. This is a magnifying glass. Your object is between the focal length and the center of the lens, and the image will be formed on the same side of the object. So this is again your image. You call it eye. Okay, so this is how you form your image. And also, the best, another good way is to, when it comes here, so denser to rarer, draw a normal here and a little bit shift, not just completely straight line, a little bit bend away from the normal, and make sure it goes like this. So this is how you draw your image or complete this answer. Similarly, underline all the words that describe the image form. So this image is, first of all, upright, and upright images are generally virtual. So these are virtual. So this is the answers. So next question, sorry, question number 6. It says the student moves a metal bar upwards between two poles of a magnet as shown in figure 6.1. So these are our magnet points. Sorry, poles of a magnet, north pole, south pole. This is a metal bar. So an ammeter is connected to the metal bar, shows a positive reading on the bar. Okay, that is interesting. Explain why there is a reading on ammeter. So remember, uh, you are moving a conductor in a magnetic field. So when a conductor is moved in a magnetic field, current is produced. So again, use the left hand rule. So this is the magnetic field direction. So magnetic field direction, your middle finger of your left hand points towards the magnetic field. Your thumb points towards the direction of movement, and your first finger will point towards the direction of current. So the current will be in this direction. So ammeter will show off deflection. So explain why there is a deflection on ammeter. So what is happening? So as a metal conductor is moved inside inside a magnet, the metal conductor is moving in a way that it cuts the magnetic field lines. So or thereby there is a change in magnetic flux. That change in magnetic flux produces EMF, or if we have a connected circuit, that EMF translates into a current. So let's write it down. The movement of metal bar results in cutting of magnetic field lines, thereby producing change in magnetic flux. This change in magnetic flux induces EMF, in which results in current flow across the bar, and that current flow is detected by the ammeter. So next part, it says complete table 6.1 by stating what ammeter shows when the metal bar moves in the direction shown by the arrow. So, so now again your magnetic field lines are in this way. Your bar moves down. So the direction of current will be opposite to what we have seen earlier. So this will be the direction of current. So ammeter shows deflection opposite to what was observed in figure 6.1. Now similarly, now the bar is moved in this direction, so no deflection, no deflection is there. The reason is no cutting of line, or you can say that movement of bar is parallel to magnetic field lines, no cutting of magnetic lines. So it does not cut the magnetic field lines, moves parallel to the magnetic field lines, and it results in no deflection. Similarly, your bar is now moving in this fashion. So again, there is no deflection, no deflection because again, because no cutting of magnetic field lines. So just simply as the movement, it produces no flux change, no cutting of magnetic field lines. So the answer will be no deflection. So the two of these cases will not show any deflection on the emitter, whereas one case will show opposite to what that so deflection opposite to what was observed in figure 6.1. And again, the reason is the change in magnetic flux that is produced by the movement of coil, movement of the metal rod. That movement that basically generates EMF uh, in the rod, and once the circuit is completed, that EMF results in flow of current, and that can be measured with the help of an ammeter. Next part. So says a student finds that using a stronger magnet increases the reading on the ammeter. Okay. State one other way in which student can produce a larger reading on ammeter using the same rod. So the other way is that uh, to increase the speed of the sorry increase the speed of the rod. The speed of the rod, or you can say that use a bigger magnet. But this bigger magnet part is, you can say that it also covers the stronger. Bigger magnets are generally more stronger magnets. But again, magnetic field strength can be increased for those magnets. But anyways, so the best answer would be the first one. This use a bigger magnet. I mean, yes, you can write it if it's a 1 point question. Examiners will give you good credit for that. So describe how Lenz's law applies when the bar is moved upwards. So the Lenz's law basically states that electric current flows in a direction such that it opposes the cause producing it. So here in the case, we can write that induced electric current is produced, or current flows in the direction such that it opposes the movement of the metal rod. That's it. So, and the movement of the metal rod is actually the cause producing it. So we can write that the induced current flows in the direction such that it opposes the movement of the metal rod. So this is the way we can write it as. So next part, next question. Question number 7. It says two circuit components. One is a thermistor, one is a light dependent resistor. For each of these components, what causes the increase in resistance? So, for a thermistor, decrease in temperature is a cause of increase in resistor. However, there are certain materials or there are certain thermistors which are available in which the resistance increases with the increase in temperature, but generally decrease in temperature increases the resistance of a thermistor. So light dependent resistor or LDR. So for this case, decrease in intensity of light increases the resistance. Okay. Next part B. It says figure 7.2 shows a battery connected to a diode, an ammeter, and a resistor. So this is your diode, this is your ammeter, and this is your resistor, and this is your battery. This is positive terminal, this is negative terminal. The graph shows a graph of voltage on the graph. So remember the diode is forward bias. So positive is connected to positive terminal, negative is negative. So the circuit or the current flows in the circuit. So diode is forward. So the current in the resistor is 2 amperes. So the current is 2 amperes. So I is 2 amperes. And the potential difference across the resistor. So VR, I call it as 5.4 volts. So if I'm measuring potential difference, so the potential difference is plus minus 5.4 volts. State what is meant by the electromotive force. So electromotive force is the amount of work done on a amount of work done per unit charge. So this is the electromotive force. So electromotive force is basically the amount of work done in moving one unit of charge from one point to the other across the circuit or from one end to another end of the battery. But in general, amount of work done per unit charge is the definition of a electromotive force. Again, explain why EMF of the battery must be greater than 4.5 volts. So remember, so in this circuit, what is happening? So there is some voltage drop across the diode, V diode, we can call it as, so V diode will drop some voltage will drop across this resistor. The battery will have also some internal resistance, and there is some negligible loss across the wires that are connecting these things together. So all these voltage drops must be compensated by the battery. So in order to have 5.4 volts here, our battery must be supplying more than that. So basically how explain why. So to supply 5.4 volts at the resistor, the battery must compensate for voltage drop across the diode. One part, its internal resistance, and drop across connecting wires. So we can write that V battery equals to VR, we call it as VR plus V diode plus V internal battery plus V wires. So this is the way you can say that, or in this way, the battery must be uh, big enough or must be having potential difference or EMF large enough to supply all these values in order to move charge from one end to its other end in a circuit. So next question, next part number 3. Calculate electrical energy input to the resistor in 5 minutes. So electrical energy, so energy, remember energy equals to charge times voltage, and charge is, and remember Q equals to IT. So what we get, energy equals to IT into voltage. So my voltage energy input to the resistor in 5 minutes. So uh, your voltage was voltage across the resistors 5.4 volts multiplied by the current through the resistor 2 multiplied by 5 minutes. Remember time is in seconds, so 60. So we multiply all these things together, you get 2 multiplied by 5, 2 multiplied by 5 multiplied by 5.4 multiplied by 60. So something around 3240 joules. That is the energy. So overall energy input 3240 joules or joules. So this is the amount of energy that is required. So let's say now part number 4, it says the circuit is reconnected with a diode in the opposite direction as shown. So in this case, the positive of terminal is here and it's connected to the negative, and this is positive of the diode. Explain what is observed. So nothing is observed. So no current flows. The ammeter shows no reading. So no current reading on ammeter because the diode is reverse biased. See? So basically no current flows through the circuit. So that would be enough as our answer. So next part, section number B. So in this section, we have to answer two questions from this section uh, in the space provided. So question number 8, it says, figure 8.1 shows a stationary horse and its rider about to jump over two fences. So this is a stationary horse and it has to jump over these two fences. Okay. So figure 8.2 shows a side view of the horse. On figure 8.2, draw and label forces acting on the horse. Include the force that rider exerts on the horse. Label this force as F. So horse, so the weight of the horse, for example, is acting downwards. So weight horse. So and weight of the and this, for example, the person is sitting on the saddle. The weight of the person or the force of the rider exerted on the horse is something like this. So call it as force F. What else are the forces acting on the horse? So there is it is standing still. So every foot will, there is a weight, is all these weights which are acting downwards are distributed across these feet. So we call it as force reaction. Uh, this we call it this, and this. So these are the reaction forces that are acting on the horse as well. So now explain how Newton's third law applies to force F. So the Newton third law, it says, so basically it says that to every action there is an equal and opposite reaction. So the horse applies equal and opposite force to the rider as per Newton third law. So the horse applies, sorry, applies equal and opposite force on the rider as per Newton's third law. So, so the opposite force will be explain how Newton third law. So the horse applies equal and opposite force on the riders as per Newton third law. An upward reaction force will be an upward reaction force will be applied by the horse on the rider. So this is how we can easily explain this thing. Next part, part B. Part B, it says figure 8.3 shows a side view of two fences. They both have same height and a uniform density. On each fence, mark the cross, mark with a cross the center of mass. So for example, the center of mass is somewhere in the middle. And for this, we see that the base is a little bit wider. And if we want to find out the center of mass, it would be somewhere here. It would be on a lower side. Explain why the wider base makes the fence more stable. So wider base, why the fence more stable? It's very simple that if we have there, I mean, if remember, you have to answer it for 2 points. So first thing, number, the center of mass is lower. This is for A, this is B. For B compared to A, comma, making it more stable. 1 point. Number 2, if we apply, so if horse will be, jumping over it. So if there is some force applied here and same force applied here, in order for A or B to topple, you need to apply larger force, and that basically says that a larger tilt angle is required, and that force will basically do what? It will tilt this uh, bar on an, say, angle. So larger tilt angle is required for B to fall. So that is another reason for more stable or more stability for the base, see the fence under consideration in part B. So this is what we can also write here. So B requires larger tilt angle to fall compared to A, right? So we can also write this. And so basically, lower center of mass and larger tilt angle are the two main reasons why uh, uh, the shape B, which is having wider base, is more stable. Next part, let's say the total mass of horse is 520 kilograms. As they approach the fence, the horse and the rider have total kinetic energy of this. Calculate the speed. So remember, kinetic energy Ke equals to half mv square. So we can easily say that kinetic energy is 4000 joules. 1 by 2, mass is 520. Remember, mass of horse and rider combined mass is given, so that is fine. V square. So V is, we can find out V from this equation. So eventually we get 3.9223 meters per second. So our speed, we can write 3.922. Again, units are very important, meters per second. This. Similarly, the center of mass, the next part, question number C, part 2. The center of mass of horse and the rider is 1.4 meters above the ground. So for example, this is your, this is, say, for example, horse and the rider in a very crude manner. I'm sorry for my drawing. And the center of mass is somewhere 1.4 meters. And say this is your base, and it has to jump over it. So the maximum potential energy gained by the horse and the rider as they jump over the fence is 3000. So the potential energy gained is 3000 joules. Calculate the maximum height above the ground of the center of mass during the jump. So the energy gained, so if he has to jump over it, so the horse would be, falling this path. So this is already 1.4 meters, the center of mass, and if it's jumping over it, so jumping over it will cause the gain in potential energy. So from gain in potential energy, we know that potential energy is given by mgh. So m, mass and weight, so 520 multiplied by acceleration due to gravity is 10, and height is something we need to calculate. So and if we calculate the height, we can estimate the uh, overall height from the, so height from here is around 5.767 meters. So this is the height that is gained because of the gain in potential energy or jumping over the block. So actually what is happening to the center of mass? So center of mass is already 1.4 meters high, and then when the horse jumps, this basically center of mass also moves up by the height. So the overall, you can say the height required, height is 1.4 meters plus the height h plus h, and that is 1.4 plus 0.576. It is approximately 1.976 meters. So you can say that approximately 1.976 up to 3 decimal places is the right answer, or the best scientific method. Some, will say approximately 2 meter is good, but generally it's good to say 1.976 meters. Overall, the maximum height above the ground of center of mass during the jump will be 1.976 meters. Next part, question number 9. Question number 9, it says, it gives us a IV curve. So IV curve, or voltage or current voltage curve for a filament of a lamp. Remember from our MCQs, multiple choice questions of the same exam, there was a IV curve for a filament of a lamp. This was something like this. So this is somewhat similar to that. Okay, so this is an IV curve given to us, figure 9.1. Now in part A, it says figure 9.2 shows complete the circuit. An incomplete circuit of the circuit that a student uses to obtain the readings on the graph. Calculate the circuit diagram using suitable circuit signals for the lamp, voltmeter, and a variable resistor. So remember, the symbol of lamp can be, again, this is the filament, this is the symbol of a lamp, or in some cases a lamp signal is like this as well. But it's good if you draw this. I mean, any two of them would be good. A symbol of a voltmeter is this, and a symbol of a variable resistor is, remember, there is only three. You have to go up and down, or this, one, two, and three. And this is a variable resistor, sometimes like this as well. So this is a symbol of a variable resistor. So use these symbols to find. So this is our battery, this is our switch. So we have a variable resistor like here, this. Then we have our lamp, and connect the circuit together. This is lamp, and if we are measuring voltage across the filament, so we have to use the voltmeter in parallel across the lamp. So this will be my equivalent circuit. So again, this is my variable resistor, this is my lamp, this is my voltmeter, this is my variable resistor. Okay, next part. The ammeter used by the student has ranges 1 to 10, 0 to 1 ampere, 0 to 100 milliampere, and 0 to 10 milliampere. Describe how the student uses these different ranges to obtain readings which allow all 9 points to be plotted precisely on the graph using the ammeter safely. So let's go on the graph. Okay, so let's go on the, oh, sorry. Oh, so let's go on the graph. So let's go. So here is our graph. So on this graph, we see that there are 9 points: 1, 2, 3, 4, 5, 6, 7, 8, and 9. Let's label them A, B, C, D, E, F, G, H, and I. So the value of A, which is measured, that is around 2.25 amperes, until we go to point, or first 4 points, they are around something between 2.5 to zero point 0.8 amperes ish. So first 4 points from point A, B, C, and D. And then all the points are from E to I. All the points are in the range 1 ampere to 1.8 amperes. So these are our ranges. So 0.2 and 0.1, 1. So now we can use them to decide what are what. So between, so for range 0 to 10 amperes, points E, F, G, H, and I can be precisely measured. Similarly, for range 0 to 1 amperes, points A, B, C, and D can be precisely measured. And similarly, uh, for or range 0 to 100 milliamperes and 0 to 10 milliamperes is not required because we do not have any measured readings in this region. So the student can easily use the range 0 and 10 for measuring the top 5 points, and for range 0 to 1 point A, B, C, D can be measured precisely. And always it is good to write these or C labeled points on the graph. That will also help your cause. Or write, this is a good way to write this answer. So now it says figure shows that the lamp does not obey Ohm's law. So how, how does, or state how, so with Ohm's law is states that voltage and current are linearly related, that is V equals to IR. Equals to IR. So the current and voltage are linearly related. The graph shown is not linear, i.e. or a straight line. See, so this is how we can say that the graph shown is not obeying the Ohm's law. Next part, question 9, part D. So determine the resistance of the lamp when voltmeter reading is 4.4 volts. So at 0.4 volts. So voltmeter reading 1, 2, 3, 4. At 4 volts, my reading is 0. Approximately 0.5. So voltmeter. So V equals to IR. So using our graph, we see that at voltage equals to 0.4 volts, I is approximately 0.5 amperes. Okay, so my resistance is V divided by I. The resistance is approximately 0.8 ohms. So the resistance is 0.8 ohms. And you can 0.4 divided by 0.5, approximately 0.8. Similarly, so using graph at voltage equals to 6 volts, my value of I is, my value of 6 volt, my value of I is 1.8 volts approximately. So value of I is 1.8 amperes, sorry. So my resistance becomes V by I, 6 divided by 1.8. Resistance is 3.333 ohms. Resistance is 3.333 ohms. Okay, so next part E. Explain why the resistance of lamp changes uh, as the voltage changes. So remember, the resistance of lamp changes as the voltage changes. So we are seeing that the voltage changes, the current in the filament also changes. So the current in the filament also changes. It produces I square R losses that heats up the filament. So heating of the filament results in change in temperature. As the temperature increases, the resistance of the lamp increases, of the filament increases. So basically, increase in voltage, comma, increases current in the filament. This increases I square R loss which results in increase in temperature of the filament. So increase in temperature of the filament results in, so increase in temperature results in increase in resistance of the filament. So this is how we can explain the increase in resistance of the filament with the increase in voltage. So next, state how the resistance of a wire depends upon the length and how it depends upon the cross-sectional area. So remember, the resistance is directly proportional to rho L by A. Rho is the resistivity, L is the length of the conductor, A is the cross-sectional area. So resistance is length directly proportional. Cross-sectional area inversely proportional. Right? So next part. The student obtains a long sample of the same type of wire as filament in the lamp. He obtains the wire he obtains has a same cross-sectional area. So area of the wire is same. Again, remember resistance equals to rho length per unit length over area is the same. So the cross-sectional area is same. He and the rho is also same. So the resistance is directly proportional to, or so basically is, we are mostly, this is constant, so concerned with the length at the moment. He cuts 1 meter length of the wire and measures the resistance at room temperature. So at room temperature, so this is a key here. He obtains a value 16 ohms. Use an appropriate resistance from D to estimate the length of the filament. So remember, at room temperature, the temperature is generally, temperature is low. So temperature is low. So it means that resistance is, so if we have to select a resistance, we have to select a lower value of resistance. So now we go to the graph and see what is there. So we see that till this point, till point C or till point D, we have almost the filament starts working or the bulb is working, and then we have there is a rapid rise in the current, and as the voltage starts increasing. So eventually it's good practice to use a lower value of resistance. So what is this question is saying? So value of resistance from part D. So we have to use this. So the lower value of resistance, the lower value of resistance is 0.8. So we'll be using this value, 0.8. So since it's using D1, that is resistance equals to 0.8 ohms. So now we have to estimate. So first, what is the value the student has measured? So student has measured a resistance of 16 ohms for a length of 1 meter. So resistance equals to, is directly proportional to length, and we can say that resistance is K times length. So from here we can find out this proportionality constant K. So resistance is 16, K is, we have to find length 1, so K becomes 16 ohms per meter. Now for the filament, the resistance is 0.8 ohms. We have to find the length of the filament. So now use simple, again, R equals to K times L. K we have calculated as 16 ohms per meter, and the resistance value is 8 ohms. So length we have to find out from here. So length is zero point 0.8 divided by 16. This is meters. So this is 0.05 meters. So my length will be 0.05 meters. And this is the estimated length, and this is how we're going to solve this question. So next part. So question number 10. Question number 10 says there is a table 10.1 contains details about nature and some properties of alpha, beta, and gamma emissions. Complete the table by filling the missing details. So nature, alpha particles, 2 protons, 2 neutrons. The charge on alpha particles. What is the charge on alpha particles? So alpha particles are positively charged, 2 neutrons, 2 protons. So this is a pos, po 2 positive, 2 plus positive charge. Okay, and penetrating power of alpha particles. So alpha particles can be stopped by a by paper, uh, stopped by a thin metal film, thin metal film, uh, air, say up to you can say 10 centimeters of air is enough to stop. So this is the penetrating power. You can write these things. So beta particle is an electron. Remember this is so alpha. You remember 4 to beta 0 minus 1 gamma as such. It is these are the symbols. So beta particle is one electron, and gamma particle is electromagnetic wave. Gamma particle is an electromagnetic wave particle. You can say wave or wave particle. So negative stopped by this. So gamma particle again has no charge, don't have any charge. Stopped by a piece of lead. Stopped by, so you can say uh, 2 inches of lead can stop gamma radiation. Few meters of concrete. Few meters of concrete can also stop gamma rays or gamma particles. So this is how we going to, or this is how the table will, a complete table will look like. Next part. Next part says that the surgical instruments in a sealed plastic bag are placed in thin plastic boxes. A conveyor belt takes the boxes close to cobalt 60 source, which sterilizes the instruments. Okay, so this is the cobalt conveyor belt. This is a cobalt 60 source, thick concrete surgical instruments. What is meant by an isotope? Isotope, same number of protons, different number of neutrons. So describe what is meant by an isotope. So these are the isotopes are two or more atoms with same number of protons but different number of neutrons. So this is what is meant by an isotope. Then suggest a property of gamma radiation that enables it to sterilize the instruments in the boxes. So these are high energy and penetration strength. High energy, these are high energy particles. Ionization, they causes ionization as well, and they have good penetration power. Uh-oh. Uh-huh. Mhm. So uh, let's wait for a moment. Yes. So some of our information lost, but anyways, so suggest a property of gamma radiation that enables it to sterilize the instruments in the bags. So ionization, high energy, and penetration strength. So these are the properties of gamma rays that helps us to sterilize instruments in the medical instruments in the boxes. State why the source emitting only alpha particle cannot be used in this manner. So the alpha particle, weak penetration strength, and they cannot penetrate uh, the uh, the packing of the instrument which we need to sterilize. So that is why we cannot of alpha particles. They cannot reach the utensils inside the boxes which we need to sterilize. Then comes the half-life of cobalt 60 is 5.3 years. Explain why the source with a half-life of 5.3 minutes is unsuitable for this application. You have to replace the source after every 5-3 minutes. So, so basically we have to replace the source more often. Replace the source more often. This is costly and time consuming for an industrial application. So that is why we need a half-life, a source or a half-life it has more than 5 years or more. Then part C. It says Giger Marsden performed an experiment in which alpha particles were fired in a thin film of gold. Figure 10.2 shows an alpha particle passing close to a nucleus of an atom. Explain why alpha particle is deflected. So remember, alpha particle is a heavy particle with a four to two protons, two neutrons, and a positively charged. And again, nucleus of gold, nucleus is also a positively charged. So the two positive charge atoms come, or two positive charge particles come close to each other, they repel each other. So alpha particle is positively charged and the nucleus of gold is also positively charged. They repel each other. So that is why the alpha is deflected. Then in the experiment, most of the alpha particles pass straight through the foil without deflection. Explain using ideas about the structure of the atom why this happens. So this is why, because atoms, most of the atom is empty space with mass concentrated in the nucleus of the atom. So the particles do not uh, find anything to interact with, they most of the space is free, so you simply pass straight through until the and if they come in close proximity of a nucleus, they deflect, and that is how we can say that the nucleus is a is a charged particle, and rest of the atom is an empty space. So so this is one point we can write, and if it is of 2 points, so we can write the second point we can write as alpha particle is repelled by nucleus and rarely comes close to it. Okay, so the probability of coming closing to a nucleus is rare. So this is how we are going to write our answer. So this is the end of our exam. So if you have any questions, please feel free to write them in the chat, and I hope you have learned something from this, and I wish you best of luck for your exams. Thank you very much.